Hello, I was watching a debate on MC Toon's channel where he was debating Fung, and it was on November the 9th. So this video has pretty much been almost a month in the works. And unfortunately, I was doing a whole bunch of other stuff. I sort of lost my place and I kind of lost track of exactly what I was trying to do. So this video is not really going to be the kind of video that I had originally intended from the beginning. But I got the idea to make this video when I was watching this point of the debate. MC Toon was trying to explain to Fung about spherical excess and how for over 100 years now, surveyors would consistently measure the angles between three different locations, always exceeding 180 degrees. So if you're on the first location, for example, and you measure the angle between the other 2 points, you're going to get an observed angle between those 2 points. Then if you move to the second location and you repeat the process, you're going to get another angle as well. And when you repeat that for the third, you add all of those angles together, you're going to get an angle that consistently exceeds 180 degrees. That's not possible on a flat Earth. And because every observation anywhere around the world that is done like that, the angles always sum to be greater than 180 degrees, therefore the Earth cannot be flat. That was the point that MC Toon was trying to convey to Fung, and I'll leave a link to that debate in the description below, and I might put a card to it right about here as well. So the first thing that I wanted to do was to replicate in the computer that spherical excess. And so I created a script that lets me enter in various geolocations, and it would be represented in latitudes and longitudes. I can select which mode that I want. Am I trying to model a flat Earth? Am I trying to model an Earth that has a radius of 6,371 kilometers? Or what would happen if the Earth's radius was smaller than that at 3,000 kilometers? I started off wanting to fine-tune all of the settings, but I didn't quite get that far, so I just ended up changing it over time. So the idea was that I would put an observation point. So if I'm standing at 1 and I'm looking at observation point 2, this little speck here would be the point that I'm interested in. What I've done over time is, rather than try to fiddle with the camera, here's the observation point that I'm interested in. This orange bar that you see would be kind of like the crosshairs, and what I'm trying to do is I'm trying to get the best reading possible. And just to make it easier and not have to worry about getting the exact height of the camera, I extended a black bar above this observation point up into space like this. And finally, to make it even easier for me, I've also included these very large spheres above those observation points. And I also have this triangle as well, so that whenever I'm zoomed really far out, I can try to get that best azimuth reading for each of these points. So I started off initially by plugging in a few random latitudes and longitudes, and then I kept playing around with the azimuth readings, getting it closer and closer to the actual value, and I put it into a spreadsheet that I used for my testing. And as I kept playing with this, I went and found various algorithms and various documentation that explains what it is and how you go about calculating it. And I tried to replicate the process where, given 3 known geolocations, given the known distance between the 2 points, can I compute the spherical excess? And there was one evening in all of this mess, I thought that I had come up with something that was reasonably close, but when I came back the next day, it seemed that I had kind of lost my train of thought and I couldn't get back to where I was. So unfortunately, I think that I've got something close but not exact. And I'm not going to step through all of the math. It's going to be in this spreadsheet that I'm going to make available in the description below, so go check that out. And I've got 3 sets of observation points, and these are the locations that I have in my Pavre script. So you would come along and say, well, if I'm at set B right now, I can switch back to set A here. What I've discovered is that whenever I do that, the distances between each of the locations changes, as you would expect, as does the spherical excess change. But what I've also found interesting is that if I change the Earth radius, the distances between each of those locations changes, but not the spherical excess, and neither would the flat Earth azimuth readings or the globe Earth azimuth readings. I added these cells to compute the expected azimuth readings to plug into these variables here for my script. In this tab, what I've done is I've entered the values that I've tried the best fit using my script. This set here would replicate what MC-Toon had done in his spreadsheet that he has made available on mctoon.net. So here's that spreadsheet over here on his page, and just a little bit further down would be the surveys done with the spherical triangles that he has made available here. So in this case, if I measured these azimuth readings, it's going to calculate the internal angles, sum up the internal angles, and if I did my math right, which I'm not entirely convinced that I did, which is why I have this disclaimer here, but if I did do the math right, and this estimated spherical excess is accurate, which would represent these cells here, then depending on which set I'm dealing with, and I put this value here, it would calculate a measurement error down to an error in seconds. So using Pavre, I modeled a flat Earth, and this would be the measured angles on the flat Earth, and I may have just simply stopped at this decimal place, but it seemed close enough to 180 degrees. When I tried the same thing with this one, it was slightly higher then, but it was still relatively close, and it was not anywhere near these. So I had come up with this script, and I was still trying in my mind to get a handle on the math involved. So I decided to try a slightly different Pavre model, and this one is going to be included in the description below. I cleaned this one up. And so the idea for this is that these rods would represent the plumb line where you are, and I modeled it as if the 3 points are equidistant to each other, so that the internal angles between each of these would be 120 degrees. So if you go directly in the middle of those 3 points and you look at the one, 120 degrees azimuth would be the second one, and 240 degrees azimuth would be the second, and then finally 360 degrees azimuth would point you back to the first one. There is no radius involved here. What you're doing is you're calculating the tilt angle directly, and I've got several other settings here, but I'll include all of the animations to both of the Pavre models right about here. And so I'll end this video like this right here. Thank you for watching. I hope this helped you kind of get an idea of what spherical excess is. If you like this video, give it a thumbs up. You know what to do. Thank you for watching, and I'll see you again in another video. Bye for now.